My name is Anubhav, and today I'll be presenting an efficient semi-streaming PTAS for the tournament feedback arc set problem done in few passes. So let's just start with defining what the problem is. We first define the cost of a permutation with respect to a specific vertex set V and a weight matrix W for each ordered pair. The weight matrix W represents the adjacency matrix of the directed graph, where W, U, V equals 1 if and only if there exists a directed edge from U to V. The goal of the feedback arc set problem is to find the permutation that minimizes this total cost that's displayed in the slide here. And for tournament graphs, there is only one directed edge between every given pair of vertices. We essentially want to just find a permutation that minimizes the number of edges going backwards for that particular ordering, and we want to find the ordering which minimizes the number of these total back edges. In the streaming setting, each edge will be listed exactly once in a given pass, and this problem is NP hard even for tournament graphs as shown by alone, but we have a PTAS for tournament graphs in the non-streaming setting, as it was first presented by Warren and Schutte. So let's discuss the motivations and applications of this particular problem. Firstly, the tournament feedback arc set problem can be rephrased as the ranking by pairwise comparison problem, or the RPC problem, where we want to obtain an ordering of items from least preferred to most preferred when we are given pairwise preferences between all pairs of items, and we want to minimize the number of disagreements. This is like identical to the feedback arc set problem for tournament graphs. And this problem is very useful for Kemeny-Young aggregation problem, which is then further useful for search engine results and machine translation. One can also reduce the loop cut set problem to a blackout feedback vertex set problem to decrease the computational cost of Bayesian inference using the feedback arc set problem. So that is another application of this problem. And similar directed graph problems such as ST connectivity and strongly connected components, which we also study in this paper, can also serve as subroutines for applications such as model checking and formula verification, or data flow analysis for compiler optimization. So let's discuss some previous work done on the tournament feedback arc set problem. As mentioned earlier, the minimum feedback arc set problem is known to be NP hard even for tournament graphs. So previous results include Kavik sort and its extension given by Chakrabarti et al., who gave a multi-pass streaming algorithm that achieves an approximation factor of 3. Ilon also gave a 1 plus epsilon approximation algorithm called sample and rank that reduces query complexity compared to the PTAS, which in some ways is similar to the streaming setting where input access is limited. Another important thing to note is that Chakrabarti et al. Also get a one-pass semi-streaming algorithm using a brute force sketching methods, which takes exponential time. So the key challenge here is to obtain better bounds for polynomial time algorithms, as that is the key missing part in the current body of work. So we first present our key result of the paper, which is the first PTAS that gives a 1 plus epsilon approximation with constant probability to the minimum feedback arc set problem on tournament graphs. It requires at most O star n space if done in log n passes. Here, like the O star notation basically just hides log n, poly log n and poly 1 over epsilon factors for clarity. And furthermore, this algorithm can be modified to work in p passes as long as we give some leeway for space and say that it and allow for O star of n to the 1 plus 1 over p space. So we first want to discuss what single vertex moves are, because these are the key local optimization method that are used in the original PTAS by Warren and Schutte for the two-dimensional feedback arc set problem, and also in the query efficient algorithm given by Alon. The idea is to just pick a vertex in the current permutation and move it to another index in such a way that the total cost of the new permutation is lower. So in this example where we are omitting all the forward edges for clarity, you can only see the back edges in this particular example on this slide. The cost on the original permutation is 12 because that is just how many back edges there are. But after moving the vertex A to index 3, the total cost is now 11. So this is a cost improving single vertex move since the total cost went down from 12 to 11. So now we'll discuss some of the key insights that go into obtaining this new algorithm. Since the algorithm can only use n polylog over epsilon space, we cannot directly calculate the cost improvement that we can obtain from single vertex moves, and we therefore need to do that by using sampling. We also want to keep enough copies of these samples so that the samples stay fresh with respect to the permutation after making a single vertex move, because we want these samples to be independent of the permutation that we obtain after making a single vertex move. So in a way, we wouldn't require a new sample because the sample that we have already used is no longer going to be independent of the new permutation. Another very important insight is that in order to get a 1 plus epsilon approximation, we only need to execute strong single vertex moves. And strong single vertex moves are ones which are long and have significant cost improvement. We'll get into what long and significant here mean later on. And finally, in order to get a polylog n over epsilon passes, we make several single vertex moves in parallel so that the permutation we're working with changes less often. This is made possible due to the fact that two single vertex moves can only affect each other's cost by O of 1. So the realized cost improvement of multiple single vertex moves made at once is similar to the cost improvement if the moves were done individually. Okay, so let's go over the high-level description of the algorithm. The first step is to just obtain a 5 approximation of the minimum feedback arc set. A result by Coppersmith et al. Shows that simply sorting by in degree of vertices achieves this, and sorting by in degree can obviously be done in just n log n space and in one pass, so that is straightforward. Now, if the size of the subproblem is smaller than log n over log n, then we can just brute force through all the possible permutations in one pass by storing all the edges in that subproblem. That is also straightforward. Otherwise, we use a small sample of edges, which gives us an additive O of epsilon squared n squared approximation of the feedback arc set with high probability. And if the cost is too high, then we run the quadratic additive approximation algorithm for the minimum feedback arc set problem by Fries et al., which we show can be implemented in a streaming setting. If we haven't hit any of these base cases, we perform single vertex moves on the subproblem until the terminating condition for approx local improve is hit, which is a method that we use and we'll get into the details of. And then we'll just recurse on the two smaller subproblems in a randomized quicksort fashion by picking a pivot and just going down the two subproblems. So now let's discuss the key optimization method used by algorithm, which is approx local improve. This is the real meat of the algorithm because this performs all the actual single vertex moves. We start by creating these sample sets EVI for each vertex V, which help us approximate the cost of a cost improvement of single vertex moves on vertex V. Now we want to be able to do all the strong single vertex moves that are available on this particular subproblem. And so as long as there exists a strong single vertex moves, we keep executing these single vertex moves, which is similar to what Alon's algorithm also does. Making these single vertex moves can change the permutation enough that the new strong single vertex moves arise, which is why we need multiple sample sets for each vertex and need to repeat this process again and again. However, the number of times that the process repeats is only poly log n over epsilon, so the number of passes needed is also poly log n over epsilon. So before we get into the proof idea and structure, we need to better specify what contributes to the cost of the feedback arc set on a permutation returned by the algorithm. The total cost can be partitioned into sets beta x and alpha x, as displayed on this slide, where x is just some arbitrary node in the recursion tree and comprises of like certain subset of the vertices. Alpha x is the cost incurred at a leaf node x, and beta x is the cost incurred at an internal node x. So the idea is that we have an internal node that is split into two smaller subproblems L and R, or I guess VL and VR. Then all the vertices in VR are always going to be ahead of all the vertices in VL in any permutation that is returned by the algorithm. So this is a commitment that the algorithm is going to make, because once the partition is made in the recursive algorithm, then the right side of the recursion is always going to have vertices that are ahead of like all the vertices in the left side of the permutation, because those two subproblems are never going to interact with each other later on. Therefore, beta x here quantifies that permanent cost that the final permutation is going to have no matter what. And now one important thing to note here is that the recursive structure of our algorithm is the same as the one in Alon's algorithm. Only the base case and the local optimization method, approx local improve, are different. Therefore, as long as we make any single vertex moves that Alon's algorithm would also make, then we should be able to use the above lemma about the cost at the internal nodes of the recursion tree as proved by Alon. Here, I, like mathcal I, represents the set of internal nodes of the recursion tree, and L is the set of leaves. The above lemma essentially states that the cost induced at the internal nodes plus the minimum possible cost at the leaves is at most 1 plus epsilon times the optimal cost, and the expectation here is taken over the choice of the pivots in the recursion. This lemma is very useful since we're getting close to an optimal solution on the leaves using the additive approximation by Fries et al. Anyway. So all we really need to show now is that we make all the strong single vertex moves possible in approx local improve, and we do that in like a few passes and only polylog n over epsilon space. So yeah, this is the key lemma I was speaking about. So finally, in order to show that we make all strong single vertex moves in the approx local improve method in one pass with the O star of n space, we first know that the realized cost improvement of every strong single vertex move is linear in n, because they're long and have significant cost improvement by definition. So a long single vertex move is just one where the length of the single vertex moves, that is like the number of spaces that the vertex that we are moving spans, is linear in the size of the subproblem, and a significant cost improvement also just means that the cost improvement incurred by the particular single vertex move is linear in the length of the move itself. So that means a strong single vertex move is going to have a cost improvement that's linear in the size of the subproblem. The number of single vertex moves that the algorithm is required to make in order to create a new strong single vertex move is also linear in n. So the amount of cost improvement that the algorithm is required to make in order to create a new strong single vertex move is quadratic in n. Since the maximum cost of a feedback arc set can only be on the order of n squared, this means that the number of times new strong single vertex moves are created is O star of 1. So the algorithm requires a new sample set every time new strong single vertex moves are potentially created, because the samples that we used to make and find the first set of strong single vertex moves are now stale. They're not independent of the new permutation and therefore cannot be used to approximate the cost of new single vertex moves. But as we showed, the number of such sets that we need per vertex is O star of 1, which means that the number of sets that we need in total is O star of n as desired. Finally, since every call to approx local improve requires one pass, the entire algorithm only requires O of log n passes with high probability, one for each layer of the recursion tree, which concludes our discussion of the proof of correctness. Another key thing to note is that this algorithm can be modified to be done in p passes with O star of n to the 1 plus 1 over p space, which is similar to the trade-off achieved by Chakrabarty et al. For their 3 approximation algorithm. The idea is to partition the layers of the recursion tree in such a way that every partition is executed in one pass. Since we need to execute multiple layers of the recursion tree in one pass, we need to store much larger sample sets, which are used for approximating cost of single vertex moves. And it turns out that if we partition the layers in such a way as described in the slide here, where the size of the where we partition them based on the size of the subproblem that we're seeing, then the algorithm only requires O star of n to the 1 over p samples per vertex, which gives us our desired space constraints. Feedback arcs problem. We also explore the field-directed graph problems in the semi-streaming setting and the streaming setting and present a few smaller results. These results include a deterministic algorithm for detecting the strongly kinetic components of a tournament graph. This is done by first computing a Hamiltonian path in a tournament graph in a streaming setting using K-Vig sort. But we also present a deterministic algorithm for computing the Hamiltonian path in the streaming setting, thereby achieving a deterministic algorithm for detecting strongly kinetic components. We also demonstrate single-pass space lower bounds through communication complexity reductions for the problems of determining if a graph is strongly connected, acyclic, and S-solid connectivity. Finally, we also obtain multi-pass lower bounds for strongly kinetic components by reducing it to decision versions of the set chasing problem by Guruswamy and Onak. Thank you so much for listening. Have a great day.